Welcome to homework.
Okay, so this question is effectively asking why it is that an OH group on benzene, when it comes to electrophilic aromatic substitution, is ortho-para-directing. And specifically, they want you to show why that is using resonance structures, okay? And the resonance structures they're interested in are the resonance hybrids that you get after your double bond has swung open and added NO2. So we're just going to skip right to that. Right? I'm going to show my NO2. I'm just going to say, all right, we've got positive NO2 floating around, make it nice and easy. And we're going to show this double bond swinging open. Okay. And that's going to give us the following product. All right, so our NO2 is going to add here if we're expecting it to add ortho, and it's probably not going to add ipso, right? And check it out, right? We've created a positive charge there, okay? Well, when I've got this OH here, right, recall that I can draw a resonance structure in which this lone pair is going to come down and give us the following. Oops. Okay, so this is a totally valid resonance structure. And in a way, you can think of it as alleviating that positive charge, right? We're delocalizing that positive charge throughout the molecule. More accurately, it actually has to do with the fact that we're putting this high energy lone pair into a lower energy orbital, but that's a more advanced topic for another day. Okay, so yeah, we can totally delocalize that positive charge over the oxygen because the oxygen has a lone pair that it can donate into the ring. Well, that, makes sense why ortho is favored, right? But what about para, right? It's the same thing. It's the same thing hold true for para, okay? So let's consider that. Okay, we've got our NO2 positively charged. Double bond swings open to add. We'll assume that it's going to add to the para side. Which means we've got a positive charge here. Well, can the oxygen donate into that? Like what? Well, yeah, because we've got resonance through the double bonds in the ring, right? So here's a resonance structure that will get us basically where we ended up when we added ortho, right, with the positive charge on the ipso carbon. The ipso carbon being the carbon that has the functional group we're interested in talking about attached, right? So ipso, ortho, meta, para. Right. And you'll notice this resonance structure in terms of where the positive charge is located looks exactly like when we added directly to the ortho position, right? And so, as you might imagine, the resonance structure is going to involve the donation of this lone pair to form the double bond, yada, 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 okay? So, point being, through resonance, adding para is basically equivalent to adding ortho, okay? So it makes sense why ortho and para are somewhat stabilized, but to really hammer that home, we should probably show that this is explicitly not true if we add meta, right? Because what if we add meta and we realize we can also get to this same structure? That wouldn't prove that ortho or para are special. It would, not really help our argument. So we should show that that's not the case, right? Or at least I think we should, in the interest of being thorough. Okay, so same scenario once again. Double bond swings open, except for this time, instead of adding ortho or para, we're going to add meta. Okay. Now our positive charge is here. Well, I mean, we can see that there's no possible resonance form that will like shift this anywhere useful. So yes, there's a resonance, right? We can swing that double bond over. It's totally valid. Okay, I'm going to actually draw this down here because I didn't leave myself enough space. Okay, but this is all we've accomplished, right? Oxygen can't donate, it's too far away. It's not helpful. Okay, and there is one more resonance form we can draw. Which puts the positive charge here. But that's equally unhelpful, right? There's no lone pairs that can donate into that, right? Yes, the resonance is, stabilizing in general, but the same is true of these forms. And I didn't step through that all the way, but this isn't the only resonance form you can draw, right? We could have also shown that. Sorry, I drew the wrong thing here. Okay. Jesus, I cannot draw right now. What is going on? There, that's better. Okay, so we could also just kind of continue to push this double bond around. Okay, so the point is that no matter where you add it, you're going to get these three resonance forms, but only when you add it ortho or para can you end up in a position where a lone pair on this OH can donate in and give you this resonance form. So this is the resonance form that's unique to adding ortho or para. When you have a substituent that has a lone pair or is, somehow pi donator.